This is antenna trainer. It consists of a transmitter and a receiver. The received signal strength picked up by the receiver is shown as received RF level. This is the displayed RF level in dB microvolt. Tune is used to control the transmitter frequency from 600 to 750 MHz. Receiver is tuned at 610 MHz with a helical filter with a bandwidth of 5 MHz. Now at the RF out, a transmitter tripod is connected with the IC connector, and similarly at the receiver end, a graduated disc with a 360-degree graduation or with a resolution of 1 degree is connected at the RF in of the receiver. Now the transmitted level from the receiver is around 100 dB microvolt, and with no antennas connected, this is the noise floor of the receiver or the entire system, which is around 36 dB microvolt. That is, it cannot detect any signal below this noise level. 35 dB microvolt corresponds to, in watt in terms of power, it is roughly around in range of nanowatts. So this is a very low noise floor. Now let us connect an antenna. This is a dipole antenna tuned at around 600 MHz. So the lambda by 2, this is a 3 lambda by 2 dipole. So 3 lambda by 2 means whenever you increase the length to the maximum, it becomes 3 lambda by 2, and when you reduce the length to minimum, it becomes lambda by 4. Now at 600 MHz, 25 centimeter is the lambda by 2, so it has to be tuned at lambda by 2. Similarly, another dipole has to be tuned at lambda by 2 and connected at the receiver end. Now rotating the receiving antenna will plot the receiving antenna. Now tune the system to 610 MHz, because this receiver, this tune control goes from 600 to 750 MHz. Tuning the control very slowly will give up at a particular point maximum received RF level that corresponds to the tuning range of the receiver, that is around 610 MHz. Now you see the reading is around 58-59 dB microvolt with both similar antennas connected. Now start rotating the antenna and start noting down the readings. At 0 degree it is giving a reading of 59 dB microvolt. Now rotate the antenna by 5 degree and keep your hands or any metallic objects away from antenna and note down the reading. It is 59.3. Again rotate the antenna by 5 degree. The reading is 58.6. Stay away from antenna every time you take the reading after rotating the antenna. Likewise, keep rotating the antennas in 5 degree modes and take 72 readings and plot it on a polo plot paper. Now suppose the antenna is rotated by 90 degree, you will see a sharp fall in the reading from 58 to 40. So that is the null. Similarly, rotating the antenna by 180 degree, you will see the reading once again reaches to the same level, that is 60, because there is no front to back ratio of a for a dipole antenna. It is same. Similarly, rotating it again by 270 degree, again we will have one more null. So again the reading has fallen to 40. So 20 dB is roughly the null for this particular dipole, once we have kept the dipole away from all the metallic objects and in the center of the room. Similarly, we can use some other antennas like a rhombus antenna. Rhombus antenna is basically a long wire antenna, and if you increase the length of the antenna, now you see the reading has increased to around 60 dB microvolt, and the angle is almost acute. Changing the angle will change the gain of the antenna. Similarly, we have a 3-element Yagi antenna. Now, this is the feed element, this is the reflector, and this is director. At 600, the feed element should be around 25. The reflector element should be 1 centimeter on either side, that is, on both sides it is 27 and this is 23. You can refer to the manual for dimensions 23, 25, 27, each lambda by 2. Now you see that the previous reading was 60 and now with the dipole the reading was around 59, 60, and whereas with this 3 element it is 61.3. So one can optimize or increase the reading further by tuning the elements. Similarly, the null is around same 40, whereas it will have a front to back ratio. So here the front to back ratio is more than 6 dB, that is around 10 dB. So and a Yagi antenna should have front to back of more than 6 dB. So this is a 3-element Yagi. Similarly, we have a ground plane with reflector. This is the half of a Yagi antenna. Similarly, you have a feed element, then you have a reflector, and you have a director. So here also you see, but the polarization is vertical. So the polarization of transmitting antenna again has to be made vertical with the help of this polarization connector. Connect it and change the polarization to vertical. Now you see this is giving a reading which is less than Yagi because it is almost half of the Yagi antenna and the polarization has also been changed. Similarly, we have a 4-element Yagi. In 4-element there are 2 directors, 1 reflector. So again similarly 27, 25, 23 and 21. The last director is 21 centimeter lambda by 2. So you will see that the gain is comparable to Yagi 3 only because it has to be tuned properly. Similarly, we have lambda by 2 phased arrays. This is a lambda by 2 phase array. This is a broadside, this is vertically polarized, so the transmitting antenna needs to be vertically polarized. Each feed element is again lambda by 2. So now you see it is giving less reading in the end fire direction, whereas when we rotate it by 90 degree it is giving gain, or the broadside direction is in broadside for a broadside array which is lambda by 2. Similarly, we have look-alike array which is an end fire array, again tuned similarly to lambda by 2. Now you see this is giving gain in the end fire direction 90 degree opposite to what it was in the broadside, whereas in the when you rotate it by 90 degree it is giving less reading, that is around 40 dB only. So this is the direction of null. So again if you see the pattern, it is somewhat like figure of 8 with nulls on broadside direction and broadside direction is end fire direction. Then we have a loop antenna. Now this loop antenna is in this position, it is horizontally polarized. One can check the horizontal polarization. Now suppose we don't know the polarization. In this vertical polarization the reading is 48-45. If you rotate it vertically the reading increases to 55. So that means this is the direction of horizontal polarization. Similarly, you rotate the antenna by 90 degree and you start seeing the null. You rotate it again the reading goes back. So it behaves similar to a dipole with nulls on these two sides and no front to back ratio. Similarly, we have a 300 ohm impedance antenna. This is a folded dipole. All the antenna consists of 1:1 balloon. This is the only antenna which has 1:4 balloon. So the impedance unbalanced at this end is only 75 ohm, whereas here it is 300 ohm. So if you see this antenna, it has a gain little less than dipole, though it has to be similar, but only because of the unbalance of the 4:1 balloon. So again it will have no front to back ratio and nulls on these two sides. Then we have this antenna kit. One can make their own antenna by connecting the antenna kit here and scraping the enamel of this wire so that it fits into these connectors. One can make a loop or a dipole out of this antenna kit. Then we have a current measurement setup. In the current measurement setup, what we do, we have a voltage probe. We remove the RF pin of the receiver and connect this probe at the receiver end and start taking the readings. Now you see the reading at the center of the dipole is less, whereas as we move away, the reading increases. So that means the current, the voltage on the ends is more and at the center it is less. So that means the current is reciprocal of voltage. So current is more in the center and less at the ends. Similarly, the readings which we have taken while plotting the antenna can be stored into the software provided and the plot can be taken.